So the name of this chapter is called the limit theorems, and the limit theorems are basically giving us the ultimate results of the concepts in the probability theory if we want to move from this point to study statistics. Okay, so if you want to study statistics, if you want to have an idea about statistical analysis concept, you need to be able to understand the limit theorems. And one of these theorems, which is called the central limit theorem here, is maybe the most important result of the probability theory. And in fact, that theorem is also considered as one of the most important theorems in the whole world that changed the world. Okay, so central limit theorem definitely needs a Nobel Prize, but I don't think that it is that young. This is a very, very old theorem, the central limit theorem, and I do not exactly know to which scientist that the theorem's proof belong to, but that theorem is a very important theorem for us to understand about the statistical analysis. Now, let's start with the Markovs inequality and Chebyshev's inequality. So again, Markov and Chebyshev are two scientists. They have provided simple inequalities that help us to comment on the probabilities if we do not know the distribution. And then we are going to go through the limit theorems. We are going to learn the weak law of large numbers, then the central limit theorem, then the strong law of large numbers. And we are going to solve a few questions where we understand the application of the central limit theorem. And if we have time remaining, maybe we can talk about the random sampling procedures. We will explain what is a random sample, and we will talk about the sample mean, variance, and these kind of concepts which are going to be helpful for us in our future statistics courses. Okay, so what are the limit theorems? So the limit theorems are the most important theoretical results in probability theory and on random variables. And one of these theorems, the central limit theorem, is considered as a very, very important theorem. And by the help of this theorem, we basically create the foundations of inferential statistics. So what is inferential statistic? The inferential statistic is this type of statistical studies which want to extract information about the general population by observing a random sample from that. Okay, so you see we have a very, very large population in Istanbul, and let's just say we would like to know about the distribution of income in Istanbul residents. Okay, for the people who live in Istanbul, we want to identify the distribution and identify some statistics related to the income levels of the people, but this will require to ask the income levels of people, each of them one by one. Okay, so it is impossible to do that because there are almost 20 million people here. So what we are going to do is we are going to take a random sample from that population, and by studying that random sample, we would like to infer information. Okay, we would like to infer information about the general population, which is called the parent population, and that concept is called inferential statistics. So by studying a small sample from the or small subset to infer ideas about the general population or the superset is called inferential statistics. And that inferential statistics studies have the base or foundation which is created by the central limit theorem. So we are going to go through these limit theorems one by one, and let's start with the Markovs inequality. Okay, so Andrei Andreevich Markov, who has lived in the second half of the 19th century and in the first quarter of the 20th century, Markov has said that, and this is a very famous scientist, okay, not just because of this inequality. This inequality is just one of the products of Markov. Markov has introduced many other things in mathematical studies and statistical studies, and he's a very, very informed scientist in this area. Markov's inequality says this: if x is a random variable which takes only non-negative values, so x is a random variable which takes non-negative values, which means x can never take negative values. So x can take 0 value or positive values. Either it is discrete or continuous. It doesn't matter. The only rule is this. It is not going to take negative values. Okay. So x is a non-negative random variable. In that case, it says for any positive real value a, the probability of x being greater than a, which is the tail probability of x being greater than a, can never be greater than the expected value of x divided by a, it says. So what does that mean? You see, let's just say I give you that x is a random variable. Okay, I give you that x is a random variable, but we do not know the distribution of it. We do not know if it is continuous or discrete. We do not know its probability mass function or probability density function, which means we cannot answer any probability question about it because we do not know these functions. But according to the Markovs inequality, what we can answer for a tail probability is this. If somebody asks me, what is the probability of that non-negative random variable to be greater than or equal to a certain real value a, I can say that I cannot know this probability because I do not know the distribution functions. But what I know is this probability can never be greater than the expected value of that random variable divided by the value that you are asking me, a. So this inequality is called Markovs inequality, and this is always true for non-negative random variables. Okay, it is always true, and we can in fact prove that. We can prove the Markovs inequality. So let us assume that x is a continuous random variable with probability density function, and it is non-negative. I would be able to do the proof for the discrete case, but the discrete case is just going to be similar. And you know, if x is a non-negative random variable, then the a value here should be also positive. Otherwise, we know that if a is negative, x is always taking non-negative values, that probability is equal to 1. So for a non-negative value of a, all we need to show is what? We need to show that a times this probability is less than or equal to expected value of x. Okay? So when we multiply that probability with a, that value should be less than or equal to x. And all we need to do to show that Markovs inequality is true is to show that a times p probability of x being greater than or equal to a to be less than or equal to expected value of x. And let's show that. Now you will realize, you will see that it is very easy to show. Now, what is a times probability of x being greater than a? How do you calculate this probability? I mean, even if we do not know its probability density function, we can write theoretically it is fx. Okay, so there is, of course, if this is a continuous random variable, there should definitely be a probability density function, though which is unknown from our point of view. But if we integrate that PDF function, probability density function, from a to infinity, then we can calculate that probability, right? Now you see in this integral, a is a constant multiplier in front of the integral. We can just take this multiplier inside the integral, and that is going to change nothing, right? So instead of multiplying the result of the integral with a, we multiply the integrand with a and then take the integral. And that is going to be an integral of a to infinity of a times fx dx. Now, a, here a is the lower bound of this integral, as you can see. The lower bound of this integral. Instead of a here, if I write x itself as x changes from a to infinity, I can definitely say that the integral here, x times fx dx from a to infinity, is definitely greater than or equal to a times fx integrated from a to infinity, because a is the least possible value of the multipliers that can be taken between a and infinity. Because x changes from a to infinity, x is taking all other values other than a through the integral. However, in the above integral, we are just writing there the lowest possible value in the boundaries in the domain of the integral. Therefore, the integral that is given in the below is definitely greater than or equal to the above integral. It can never be less than that, because we know that a is greater than 0. A is a positive value, and from a to infinity, everything is greater than a. And finally, the last integral that I have written here is an integral of x times fx dx from a to infinity, but a is a positive value, as I have said. Now, instead of from a to infinity, if I calculate that integral from 0 to infinity, that integral is going to be larger. Why? Because the probability density function is not a negative function, it is a positive function, and x is also a positive function. So when we multiply these two positive functions, we get a positive function. And if you integrate a positive function in a larger interval, then the total area under it is going to be even larger. Therefore, you see a times probability of x being greater than or a is less than or equal to the expected value of x. Now, if you realize that the last integral that I have written here is the expected value of x. Now that we have proven this, if you take this a in the denominator of the expected value of x, you will realize that for a non-negative for a non-negative random variable with any distribution, any unknown distribution, the tail probability of x being greater than or equal to a. So such probabilities are called tail probabilities, if you remember. That tail probability is less than or equal to expected value of x divided by a, which means that probability can never be greater than this value. Now let's practice this. We are asked a question here about the Markovs inequality. Suppose that it is known that the number of items produced in a factory during a week is a random variable with mean 50 units. Okay, so in this production line, we are trying to manufacture products, but from week to week, the values are changing. Not every week we are able to manufacture 50 units, but what we know is, on the average, we can manufacture 50 units per week. So we only know the average value. We only know the expectation right now. Nobody is telling us anything about the distribution of the number of units manufactured. Okay, so we do not have any information about that. But the question is asking me this: what can be said about the probability that this week's production will be at least 75 units? So basically, the question does not provide me any probability density function or cumulative distribution function, or if the production quantities are given in the discrete units, then it does not provide me any probability mass function. These are unknown. But what I know is the number of products manufactured during a week is a non-negative random variable. So if we say x, the production quantity per week, is a random variable, x is a non-negative random variable. I mean, you cannot manufacture negative units, right? And the expected value of x is also known to be equal to 50. So I can use the Markovs inequality because I have enough information. Now, the question tells me this: what can you say about the probability of the next week's production to be at least 75 units? So what can you say about the probability of x being greater than or equal to 75? Now, I know that the tail probability of a non-negative random variable can never be greater than expected value of x divided by a. The expected value of x is 50, and that a value asked in the probability is 75. So what I know is that probability, the probability of having the productions of the next week to be at least 75 units, is never greater than 2/3. So I cannot say anything, I cannot compute that probability, but I can say that it cannot be more than 2/3. Okay, so Markovs inequality basically helps me to identify a upper bound, identify an upper bound for the tail probabilities of non-negative random variables. So we can only say that 2/3 is the upper bound for that probability. That probability is either less than or equal to 2/3.